In this video, I would like to talk about feedback effects from trading. Let me start with specifying what exactly we are going to discuss here. It's known that large trades on stocks move the market. Therefore, we need to incorporate such effects in our stock trading models that we apply for portfolio of stocks if we really want to deal with such big trades. We talked about how such effects for stock trading in the last week of our previous course. And now I want to talk about price impact effects from stock trading as applied to option trading. A link between these two topics is provided by the fact that an option derives its value from a stock, and it's also hedged by the stock. Now, this video is based on a few papers that I recommend if you want to know more about models of such type. One of them is a model by Lee and Almgren from 2016 called Option Hedging with Smooth Market Impact. This paper deals with intraday hedging of an option position by a large trader who has to worry about market impact of trades made in a hedge portfolio of the option. Almgren and Lee tell the following remarkable story. On the morning of July 19, 2012, an unusual sawtooth pattern was observed in U.S. equity markets. 4 large stocks exhibited substantial price swings on a regular half-hour schedule. Each stock hit a local minimum price on each hour and a local maximum on each half hour, as shown in this figure on the slide. Now, no significant news were released on this day, but CBOE options expiration was the next day. Now, the most plausible explanation for this phenomenon is that this was the result of a delta hedge strategy executed by a large option position holder with no regard for market impact. Each half hour, he or she evaluated the necessary trade to obtain a delta neutral position and executed this trade across the next half hour. Market impact caused the price to move, and at the next evaluation, the new price, the position was partially reversed. And in fact, this action is quite similar to forward Euler discretization of an ordinary differential equation, which can introduce instability of exactly similar sort. Similar phenomena were also observed in treasury markets. So what this phenomena demonstrate is that there are feedback effects from the option market to the stock market. Such phenomena cannot be explained by standard models for option prices, such as the Black-Scholes model, or its straightforward extensions, because in this models, a stock market drives an option market, but not vice versa. A closely related effect is the so-called stock pinning. Pinning at a strike refers to the likelihood that the price of a stock coincides with the strike price of an option written on the stock immediately before the expiration date of the option. A graph that you see on this slide is taken from a paper by Avellaneda, Kassian, and Lipkin from 2013 that extends a model proposed by Avellaneda and Lipkin in 2003. This graph schematically shows trajectories of 2 stocks, A and B. Stock A does not have an option, while stock B has an option with strike of 1,250 cents that expires on the 3rd Friday of the month. As this graph illustrates, the price of stock B coincides in this example with the strike of the option at the option expiry date. In real markets, this phenomenon can be a bit less pronounced. so that the two prices would not exactly coincide, but still would be very close near the option maturity. And this is why this phenomenon is called stock pinning. The stock price may become pinned at the option strike when there are minutes left to the, or less than a day left to the option maturity. And this is very remarkable because it provides a strong trading signal at this time. In other words, stock dynamics becomes quite predictable during such periods and therefore also potentially exploitable. The Avellaneda-Lipkin model is based on the behavior of option market makers that impact the stock price by delta hedging their positions. In their first paper, they considered a linear impact function, while in the second paper, they extended the analysis to a general power law. The impact model that they analyzed is shown in the formula on this slide. It says that the price impact, or a relative change of a stock price, is proportional to the size of the trade delta x raised to power p and multiplied by an elasticity parameter E. What they found is that there are qualitative differences in the model behavior for different values of parameter p. If p is less or equal than 1/2, there is no pinning phenomenon anymore. It only exists if p is larger than half. And using the language of physics, this means a certain phase transition in the system, in the sense that the behavior of the model is qualitatively different in these two regimes. And this result implies, in fact, something very profound, that the classical financial theory that corresponds to the limit when p goes to 0 is likely to be a non-analytical limit. This limit describes a different system from the actual financial markets. And finally, I want to briefly mention a few more related models. The first one is a model of smooth hedging with market impact by Lee and Almgren from 2016, which I already mentioned earlier. They built a model similar to models for optimal stock execution that we discussed in the first week of the previous course. In their setting, a target portfolio is defined by the value of the Black-Scholes delta. A risk function is quadratic and is based on a Markowitz-like mean variance analysis, the same approach that was used in the QLBS model that I presented earlier. While Lee and Almgren focus on analytically tractable settings, a similar framework, but with a more general setting, was developed by Guyan and Pu in 2015. Their approach relies on a utility-based approach and amounts numerically to solving an HGB equation, which is computationally heavy. And all these topics that we discussed in this lesson finally bring us back to what we started with in this lesson, namely reinforcement learning. As the whole field of using reinforcement learning for option pricing and hedging is still in its infancy, there are no yet papers that would compare reinforcement learning with classical methods on these types of tasks. But at least the direction of how it can be done is shown by a simple framework of the QLBS model that I presented in the previous course. This model uses a very simple quadratic utility that does not take into account feedback effects and transaction costs, but it can be extended in a straightforward way to incorporate these effects. Indeed, feedback effects are in general assumed in reinforcement learning tasks. And adding market impact and transaction costs simply amount to modifying the reward function in the reinforcement learning setting, keeping the rest of the methodology intact. And this is exactly why reinforcement learning appears to be a very natural and computationally attractive approach to option pricing, hedging, and trading. And on this note, I would like to round up this week of our course. And in the next week, we will finally leave the option world and talk more about the stock world. See you there.